Hey guys, my name's Ethan with GoBuilda, and today we're going to walk through using servos and FTC. Today we're going to talk about position control servos. Some servos are continuous rotation, where instead of controlling the exact angle it goes to, you control the direction it moves and with how much power it moves in that direction. Our dual mode servos can actually do both if you have a servo programmer, but today we're going to talk all about their positions, how to set those positions, and how to find the right range for your servo. My favorite thing about servos is that they always remember the position that you program them in. Here we have a servo block and I have a mark on that servo output. We can rotate this by hand, and it doesn't matter where we rotate it to. As soon as we plug this servo back in, it's going to rotate it so that that mark is facing straight forward. That's because it has an absolute position reference. This uses a potentiometer, but some servos use encoders so that they can point that spline always exactly forward. Something like a motor is relative, so when you power it on, its encoder can track how far it's moved, but it doesn't know where it is absolutely. So if you start a motor's encoder here, it doesn't know that that's any different of a position than starting that motor here. A servo, on the other hand, will always remember where you leave it, so they're really good for something like a wrist, where it needs to go to an exact position, and that position never changes. It's really handy to just be able to turn on the servo and have it go right to that position. We can really take advantage of this absolute positioning of these servos with some careful thought into how we attach components to them. Because servos have multiple teeth on their spline, they either have 24 or 25 teeth, we have a bunch of different orientations we can put the servo attachment onto the servo in. And that changes where that mechanism is relative to the servo. Here our servo is sending a centered signal. We have a lot of signal to the right and a lot of signal to the left, so we have a lot of motion in either direction. And we can choose, do we want that mark to be forward, do we want it to be toward the left, or to the right? Here's a great example of when that is handy. Here we have the starter kit robot for this year's First Tech Challenge season, and it has a wrist that rotates left and right with a position control servo on it. Now, if we keep track of where that servo is initialized, where it thinks is home, we can then install the servo onto the arm in an orientation that means it's really easy to keep track of the positions we care about. Next up, we're going to put this principle into practice. We have an absolute servo that always remembers its angle, and here I have a servo that I've just installed in this servo block. I don't know exactly what position it's in, so I don't know what it thinks home is, and I don't know how to correspond the angle of the servo to the angle of the wrist. We have a piece of code that's pretty simple. We call it the servo position helper. This lets you find both the center position of the servo and any positions you need to move the servo to. And today we're going to use that to find two positions. We're going to set our wrist folded out position, so straight in line with the arm, and we're going to set a position that is rotated 90 degrees in. Now, because I've rotated this servo and I don't know exactly where that center position is, we're going to initialize this code. This sends it a position of 0.5. In FTC, we control servos as a position between 0 and 1, so 0.5 is right in the middle, and that gives us some range both left and right of the servo's home or center position. Now, there really isn't anything special about 0.5, but I like talking about the center of a servo's travel a lot, because I think in a lot of applications that's the most important piece. You might have an application where the most important position to you is all the way in one direction, and then you might change the reference point you have. But the important thing is that you know where in the servo's travel you're mounting the servo horn on. You don't want to mount this all up, turn on your code for the first time, and have it move to somewhere it can't reach, or totally uncontrollable. So here we have a servo that's on, it's holding its position, but we haven't hit start on our code yet, so there isn't any way for this servo to do something unpredictable. Now, we've picked 0.5, and the most important position for our arm is when it's folded out straight alongside the arm. This is for when we go intake samples or specimen, and we're going to slot the servo into that hub and find the set of teeth on the servo spline that align best in line with the arm. So that's slotted in nice, and now we have a set position. What we can do now is grab our servo screw and our 2.5mm hex key and put a screw in that so it stays in place and we don't lose that position. We have our servo screw, and it's also nice to install this servo screw at this stage because the servo is holding its position. So it lets us apply a little bit more torque to this servo screw without the servo just rotating. We can tighten that up just a little bit, and now that servo is solidly in place, and we can start finding that second position. The next thing we'll do is hit start on our op mode. Now right now we're sending that same 0.5 signal to our servo, and we can click the A and Y button on our gamepad to increment or decrement that position that we're sending it. Here is our 0.5, and we might still tune this a little bit by finding slightly nicer positions, but for right now we're going to find that secondary position. The next one we want to find is when the servo is rotated about 90 degrees inward, so that wrist is folded in and out of the way of any other game elements. It lets us fit in the 18-inch cube in this specific application. Now this is folded in, and over on our driver station, we can see the position that we're sending the servo. This is printing that in telemetry, and we can see that this position we've sent right here is 0.9. And now we have another position in our repertoire that we can put in our code to move that servo to exactly where we want it. Now we can change the step here and fine tune that position. If I want it to be closer to 90 degrees, we'll rotate it out a little bit, but I think what we found is pretty reasonable. You can use this example code to find the specific position you want to move your servo to, and critically, this lets you think about using positional servos in a way that's really productive. If you have to replace this servo, before you just go and install it, you should plug it in, initialize your code, and find the place that it wants to be, and you can know how that corresponds to the angle of the mechanism you're attaching. If I was going to replace this, I would initialize this code, move that servo to the center point again, and then install the mechanism with that known position. Now this is a really nice way to find servo positions with this code, because all you have to do is turn on op mode, move your servo until you see that it's in the position you want, see what it tells you in telemetry, and go write that down. It's really easy to find the correct number, and it allows some imperfections in the system. If you are trying to move exactly 98 degrees and you have a hard stop, calculating that number isn't quite as flexible or user-friendly as turning on some code and looking at how far it's moved. It's also really easy to tell if you've hit an end stop, because the servo will start whining and you'll be able to tell that it's stalled. If you do know you want your servo to move a specific number of degrees, that's also pretty reasonable. As a spec, on almost every servo page, you'll find its maximum rotation. The maximum rotation is how far is it going to rotate if you give it the minimum signal and then give it the maximum signal. Now this will be equivalent most of the time to that 0 to 1 in your Rev Hub. You can go online, find that spec, and that will tell you how to change your code to move that servo a specific number of degrees. Go Build the Servos will move 270 degrees with a standard 0 to 1 signal in FTC. And if I want to move that servo 90 degrees, I need to take 90 and divide it by 270. I have what I am desiring that servo to rotate, and dividing it by the total rotation it can do. Now this will yield about 1/3, because 90 is a third of 270. And now I know if I want to move this servo exactly 90 degrees, I need to change its position by 0.3333. So if I start with 0.5 and I want it to rotate it at 90 degrees inward, that's the amount I need to change that. So I'll send it to 0.5 for folded out and 0.8333, 0.5 plus a third, to rotate it all the way in. Now that we've talked about the positions servos run to, let's talk a little bit about servos electrically. Servos like running on a lower voltage than the rest of your FTC robot. Your robot runs at about 12 volts. It'll be a fully charged 12-volt battery, but servos are expecting between 5, 6, and sometimes 7 volts. With an FTC, that's either 5 volts if you plug them into the control or expansion hub, or 6 volts if you use a servo power injector. Now, this lower voltage means that inside of either of these devices, there needs to be a voltage converter, something that steps it down from 12 volts to a nice 5 or 6 volts. Now these power converters have a limit to how much current they can supply, and the control and expansion hubs specifically have kind of a funky way of distributing that power. Now on the control and expansion hub, each of those you have six servo ports. They're labeled 0 through 5. So it's 0, 1, in a way that's a lot like programming. You start at the 0 and you go up until you have 6 total ports. These are split up into port pairs. So ports 0 and 1 are connected, 2 and 3, and 4 and 5. Now these port pairs all share a regulator, so you have 2 amps that you can use in any specific port pair. A lot of FTC servos can get close to pulling 2 amps. Gobilda servos, for example, on 5 volts will pull 2 amps. So having 2 servos that both have to work at the same time, they both have to pull current together on the same port pair. So if I plug 2 servos into ports 0 and 1, you can overload that voltage regulator pretty quickly, and that'll cause both of the servos to cut out and then come back. If you have something like a claw, make sure to move those servos into different port pairs so that they can both pull the amount of current that they need and not overload the built-in voltage regulators in the control hubs. Now, most of the servo power injectors are a shared voltage supply across the entire servo power injector. So if you have a servo power module, it runs at 6 volts, and every one of those ports could pull the maximum current of, say, 15 amps. We don't have to worry about which port each specific servo is plugged into. We have the maximum current available to each individual port. So in that case, about any of them work. That brings us nicely into servo power injectors. These are devices which allow you to pull both more current and they apply more voltage to your servos, meaning that you have more performance out of them. If you go from about 5 volts to 6 volts, you get a significant boost in both the speed and the torque that that servo is able to provide. Now, I talked about a shared power rail, where each of those servo ports share power. This means that they act a little bit different from the power ports that you expect on your control hub. When you hit stop on your code, your control hub is going to cut voltage to the servos. So they're going to lose power and they're going to be able to move freely. On a servo power injector, that may not be the case. A lot of them continue to supply power when the signal is cut, and that means that the servo gets to decide what to do when it loses that signal. So our servos, for example, when they have power but lose signal, still do not hold a position. They're free to rotate. A lot of servos have a fail-safe position, so that if they lose signal but still have power, they'll go to a specific position and hold there. And some other servos will hold at whatever position they last received. There are a bunch of different ways that different servo manufacturers implement these fail-safe positions, but it's important to note that when you grab that servo power injector, your servos might perform a little bit differently when your code is not enabled. They're waiting for signal. Sometimes they'll be limp, and sometimes they'll be moving to specific positions and doing their best to hold that position. So if you hear a servo moving or operating or holding a position, even though your code isn't running, that may be because you have a power injector, and that's a good thing to always keep in mind. The last thing we'll talk about today is PWM ranges. Now, we talk about in FTC controlling servos to specific positions, and we describe these positions between 0 and 1. And that isn't exactly what's happening behind the scenes. Servos operate on a control signal called pulse width modulation, or PWM. And in servo PWM, we talk about the length of that signal. How long is that signal high in a specific frequency or a specific period, right? So a servo period will be 20 milliseconds, and we're going to send a pulse where we pull that high for a specific length of time. And how long that signal is high is the instruction that tells the servo where to go. Servos almost always have their own PWM range, what they accept as the minimum and what they accept as the maximum signal length. And they map their own range to that different signal length. Most of the servos that are common to FTC, you have Gobilda and Rev servos, for example, those can accept the maximum PWM range out of the controller expansion hub. That maximum range is 600 to 2400 microseconds. Some servos, especially high-tech servos, do not expect a range that wide. So go on the website for the manufacturer of your servo and check that PWM range, especially if you get a servo that's brand new out of the box, you plug it in and your code doesn't work. It may be because you're sending it a signal that servo doesn't recognize as in range. This is one of the features that the extended implementation of the servo class in FTC allows you to do. It lets you jump in and say, I want to control a servo with this PWM range. So between, say, 500 and 2500 microseconds, or between 1000 and 2000 microseconds. You can go and talk in that language specifically because you probably have that spec from a servo manufacturer. This also lets you get slightly more range out of Gobilda servos. If you, by default, just plug them into your Rev Hub, you'll see about 270 degrees from 0 to 1. But if you go back and tell that rev hub that this servo can actually accept a 500 microsecond to a 2500 microsecond signal, you can eke out about 30 more degrees for the maximum range that we talk about on the website. Now we have this servo helper file and an example code that goes over the extended implementation of the servo class, both in the description below. I really like this code for finding servo positions. It's super handy and easy to use, and it's good to look at those different methods and different functions you can use with servos and think about how they affect your rotation. Maybe you'll limit the PWM range of your high-tech linear servo to make it more intuitive to work with for a newer programmer because it has a narrower range than a Go Build a Servo. Servos are a really powerful tool in the toolbox of many FTC teams, and if you have questions about them or other parts we sell, feel free to shoot us an email over to tech@gobuilda.com.